Hello viewers, today we are going to see Spectral Series. So this series is Balmer series in the emission spectrum of hydrogen. So before going into fine details of Balmer series, we will see some basics. We might expect that the frequencies of the light emitted by a particular element would exhibit some regular pattern. Hydrogen is the simplest atom and therefore has the simplest spectrum. So hydrogen is the simplest atom and therefore has the simplest spectrum. I already told you spectrum is nothing but range of frequencies or wavelength. But in the emission spectrum, we see a definite specified wavelength or frequency. It is not continuous. In the observed spectrum, however, at first sight, there does not seem to be any resemblance of order or regularity in spectral lines. But the spacing between lines within certain sets of hydrogen spectrum decreases in a regular way. So this is figure 12.5. Each of these sets is called a spectral series. Now if you see, this is H alpha, which is 656.3 nanometer, and then H beta, which is 486.1 nanometer, H gamma 434.1 nanometer, and 410.2 nanometer for H sigma, and H infinity, it goes up to infinity. Each of these sets is called a spectral series. In 1885, the first such series was observed by Swedish school teacher Johann Jacob Balmer, 1825 to 1898, in the visible region of the hydrogen spectrum. So the Swedish school teacher named Johann Jacob Balmer, he did research in the visible region of the hydrogen spectrum. So visible region is roughly around 300 or 330 to 720 nanometers. This is visible spectrum. Visible spectrum means the wavelengths that a human being can see. The line with the longest wavelength, 656.3 nanometer in the red. So this 656.3 nanometer is in the red region, very close to red, or it will be a shades of red. This is called H alpha. The next line with wavelength 486.1 nanometer in the blue-green. So this is a combination of blue and green. This wavelength 486.1 nanometer. The third line 434.1 nanometer in the violet. So this in the violet region. Shades of violet. It is very close to violet. And so on. As the wavelength decreases, so here we have higher wavelength and slowly it decreases. The line appears closer together. See, these lines are appearing very close together and are weaker in intensity. So here the intensity of the lines are weaker. Balmer found a simple empirical formula for the observed wavelengths. So he has given us a formula, empirical formula, that gives an idea about the wavelengths. So the Balmer wavelength, observed wavelength given by Balmer, observed wavelength given by Balmer. This is only an empirical formula. 1 by lambda is equal to R into 1 by 2 square minus 1 by n square. So this is the formula given by empirical formula given by Balmer. So it connects three terms. One is lambda wavelength, then we have R, and then n. So lambda is the wavelength. R is Rydberg's constant. Rydberg's constant, and the value of R is equal to 1.097 into 10 power 7 per meter. So meter power minus 1. And the value of n is n can take values, integral values. N can be 3, 4, 5, etc. So this is equation is also called as Balmer formula. Okay. Now we are going to solve or find out when n equal to 3. So what happens when n is equal to 3? If you put n equal to 3, so n equal to 3. So we get H alpha, this H alpha wavelength. H alpha line. So 1 by lambda. Rydberg's constant we know, you just substitute 1.097 into 10 power 7 per meter, and then we have 1 by 2 square minus 1 by n square. N we have taken as 3, so 1 by 3 square. So this will be 1 by 4 minus 1 by 9, and after simplification you will get 1 by lambda equal to 1.522 into 10 power 6 meter power minus 1. Therefore, see, you please check whether I am getting this result. 1.522 into 10 power 6 after simplification with calculator. So therefore 1 by lambda is this value. Therefore lambda by 1, that is lambda is equal to 656.3 nanometer. That's how we got this wavelength for red, or in the region of red, 656.3 nanometer. This result, this wavelength we got for the value of n equal to 3, which is H alpha. Next, for n equal to 4, if you substitute n value as 4, you will get H beta, and so on. And when n tends to infinity, when n tends to, likewise n keeps on increasing, and when it reaches infinity, 1 by infinity is 0. Therefore, you will be having r by 4. So, r by 4 is what? So 1 by lambda is equal to r by 4. This is the case for when n tends to infinity. That is, lambda is equal to 4 by r. Now we will know the value for Rydberg's constant, which is 1.097 into 10 power 7 per meter. So you will get so you multiply by 10 power 2 both numerator and denominator. So this will become 400. So 400 divided by 1.097. When this goes to the numerator, it will get nanometer. So just you calculate, students, please listen. Just you calculate 400 divided by 1.097. Tell me the answer. It should be 364.6 nanometer. This value. Am I right? Okay. That is, when n tends to infinity, 1 divided by infinity is 0, so r by 4, and we have solved for it. So you are getting the value as 364.6 nanometer. This is for H at infinity, spectral line of hydrogen atom when n is equal to infinity. Okay. Other series of spectra of hydrogen were subsequently discovered. These are known as, after their discoverers, as Lyman, Paschen, Brackett and Pfund series. These are represented by the formulae. So after Balmer has given an empirical formula, many researchers have worked in that domain, and they came out with different types of series. First, Lyman series, Paschen series, Brackett series and Pfund series. We will see one by one. Okay. Okay. Now first we will see Lyman series. So Lyman series, the formula is 1 by lambda, which is equal to r into 1 by 1 square. The Balmer series, we have 2 square, here it is 1 square, minus 1 by n square, where n can take 2, 3, 4, etc. So just if you carefully see, if it is 1, its n value starts from 2, 3, 4 like that. Okay, this is Lyman series. Then we will move on to Paschen series. Paschen series. So in Paschen series, 1 by lambda is equal to r into 1 by 3 square. So this is 1 square, Lyman series. Balmer series 2 square, Paschen series is 3 square, minus 1 by n square. Now here if you see, where n is equal to 4, 5, 6, etc. So since we have 3, n value starts from 4, 5, 6 and so on. Next we are going to see about Brackett series. So in bracket series, 1 by lambda is equal to R into 1 by 4 square. Previously with Paschen series it is 3 square, now it is 4 square minus 1 by n square, where n is equal to 5, 6, 7, etc. It goes up to infinity. Since this is 4, the n value starts from 5, 6, 7, goes up to infinity. Then we have Lyman series. Lyman series 1 by lambda is equal to R, Rydberg's constant, into bracket series starts with 1 by 4 square. So this is 1 by 5 square minus 1 by n square, where n starts from bracket series n is equal to 5, 6, 7. Here n is equal to 6, 7, 8, etc. Since this is 5, n value starts from 6, 7, 8 and keeps on going up to infinity. Now, the Lyman series. So, Lyman series just now we found out 1 by lambda is equal to R into 1 by 1 square minus 1 by n square. So, Lyman series works in the region of ultraviolet UV. So Lyman series deals with ultraviolet region, whereas Paschen and bracket series, these two works with infrared region. So you all know that the visual spectrum goes like this: 330 to 730, VIBG or violet, indigo, B, G, Y, O, R. After red it is infrared. So Paschen and bracket series gives the spectral lines in the infrared region, where